In our previous video, we introduced the concept of a yield surface for a material and used that to be able to develop a model for multiaxial cyclic loading using the von Mises criterion and something called the normality flow rule. It's a fairly standard thing to do in plasticity, is to come up with ways to look at various paths using incremental plasticity. Although we didn't go into all the great details, we just kind of introduced the concepts. I did mention that I do have other videos available and teach another class in plasticity theory where we get into those types of details. In this video, I want to talk about something called a structural yield surface, try to introduce that concept. Then we're going to go back and take a look at load notch strain approximations in the context of multiaxial type loading. All right, so with the structural yield surface, we're going to start off with just kind of considering a special case. We'll see how that works, and then we'll kind of generalize this. So suppose we have a notched bar that's in tension and torsion. So we have multiaxial loads. I didn't do a great job of drawing that notch, but it's a circumferential groove. It goes all the way around that. Now, if I were to pull on this bar, I would get a multiaxial stress state just due to the nature of the axial force and the notch. So let me draw a little cube of material here. If I were to take this cube out of a little spot right here, when I pull it on it in the axial direction, I get some axial stress, and I actually get some hoop stress in the bar as well. Now, if that notch wasn't there, then I would have pure axial stress. Wouldn't have any transverse stress or hoop stress. In addition, then, when I throw the torsion on top of it, I get some shearing stress as well. I'll just draw those two. A little subscript torsion right there. And of course, there's different ways to think of this. If this was a finite element model, then we would go through the details. If we had plasticity, we could calculate exactly what goes on there with the whole finite element routine and so forth. But what we'd really like to do is to be able to have a way to estimate what goes on at that notch root. All right, let me show another plot here, see if I can sketch this out. Suppose I were to look at the strains when I look at this. All right, so we have an axial strain. We have a hoop strain, or a transverse strain. Then we have a strain in the z direction. There's no stress in this radial direction, I guess I should call it. There's no stress in this radial direction, but there is a strain. And if I were to take a look at the ratio of the hoop strain to the axial strain, and the ratio of the radial strain to the axial strain, if this was a perfectly smooth bar, then the ratio would start off as Poisson's ratio of minus 0.3 in this case, if I don't have the sign change in here. And it would transition to minus 0.5. Okay, so I'm going to draw these plots. So it starts off here at minus 0.3, and it transitions over to minus 0.5. When we have fully plastic loading that overwhelms the elastic part of the strains, then, as I mentioned, some people call it a plastic Poisson's ratio. Sometimes it's convenient to think of that way, but it comes about due to the conservation of volume during plastic flow. Then this ratio then transitions as we start to have more and more plasticity, it kind of transitions over here and approaches 0.5. And if this was a smooth bar, then both of those lines would be on top of each other. Okay, so this is both the ratio epsilon hoop to epsilon axial and epsilon radial to epsilon axial. Okay, so this would be for a smooth isotropic material, smooth bar, isotropic material. All right, now let's consider what would happen when we have a notched bar, and we're just taking a look at the ratios of the strains. Let me make a new page. All right, there's my smooth bar behavior. Well, the presence of that hoop stress changes these ratios if we have a notched bar. Let me make the same kind of plot. So if I were to take these and let's see, the hoop stress over the hoop strain over the axial strain, that ratio should be reduced in magnitude. Okay, so I'm going to say maybe it is minus 0.2. Depends on the severity of the notch. We end up with a tensile stress in the hoop direction, which it counteracts the contraction that we would ordinarily see due to Poisson's ratio. Okay. Now the radial over the axial, that's going to change a little bit too, because we have a multiaxial stress state as opposed to a uniaxial stress state. So maybe that changes a little bit over here. So maybe I'm just going to make up a number. Maybe that's around minus 0.4. Now both of these end up in different locations as well when they transition to plasticity. So let me maybe make a little note here. This is elastic, and this is fully plastic. Move up this axis. So I'm going to draw these lines, and then I'm going to explain the numbers that they approach. Okay, so the number has to add together to be minus 1. Okay, so maybe this one transitions over to minus 0.4, and maybe this one transitions over to minus 0.6. Because of the conservation of volume during plastic flow, they have to balance against the unconstrained, well, balance against the radial. Okay, so they against the axial rather. So they both have to be minus 1, where this ratio, the axial over the axial, is equal to 1. All right, so this is large plastic strains over here, and this is elastic down here. And this is the situation where we have a bar that has a groove in it, like we have here. And again, both of these cases I'm looking at right now are in pure tension from the nominal stress point of view. All right, so when I look at this, if I didn't know that the material had a notch in it, and if I, just kind of covered up this section, and if I looked at this behavior and I looked at this behavior, this is an isotropic material, and if I were to look at this behavior, if I didn't know a notch existed in that material, I would say that is definitely an anisotropic material. Okay, so this is a notched bar with an isotropic material. And this looks like an anisotropic material when expressed in terms of the nominal stresses. And with that background, that's kind of the background for this paper, a yield surface approach to the estimation of Notch strains for proportional and non-proportional cyclic loading. Okay, so here is the multiaxial stress state that we just talked about. And if you have a material that is anisotropic in terms of the nominal stresses, then you would use a anisotropic yield criterion. And the one that I chose was the simplest one for the job. For me, that was Hill's criterion, looking at these different coefficients of anisotropy based on the different strengths. And basically what I was able to show is that these depend on the different stress concentration factors at the notch. So here's all the math and the details. This is the normality flow rule again. We can do that for an anisotropic material. And we can calculate different strains and comparison to the finite element analysis and so forth for proportional loading. And then we can do non-proportional loading paths as well. The non-proportional loading path that I used was a box shape, and as plasticity increased, the tilt of this box in terms of strain becomes more pronounced, and we can compare it to some calculations. All right, so let's talk a little bit more about this for the multiaxial response. So if we can agree that there's some sort of yield surface, and I call it a structural yield surface because it depends on the stress concentration factors. Right? And that it is anisotropic, but can be recovered to be an isotropic yield surface if the stress concentrations disappear. Then we have the same type of formulation that we had for our regular yield surface plasticity. So we have some yield surface sitting here. We have the center of it. We can load it proportionally, non-proportionally. We can do incremental plasticity. All the things that we've done before, we can use to calculate increments of notch root plastic strain. Okay, so this is in terms of nominal stresses. But the output is notch plastic strain. What do you need when you have a yield surface model? Well, you need as input your yield criterion, the things that go into your yield criterion. We said that can be expressed in terms of the stress concentration factors. That's not a big deal. But you also need a stress versus plastic strain curve. And in this case, then, since we're expressing this yield surface in terms of nominal stresses, this would be a nominal stress versus notch root plastic strain. And whatever shape that looks like. Well, how do you get the nominal stress versus notch root plastic strain curve? Okay, well, we have a few ways to do that. We have Neuber's rule. We have Glinka's formula. can use elastic plastic FEA, and we can do measurements. And all of these, all we need is one curve. Just like in regular plasticity, all we need is a stress versus plastic strain curve. With the assumption of the yield surface, then we have the complete description of our material. Here, we just need the one nominal stress versus notch root plastic strain curve with our assumption of our yield surface and the normality flow rule. Then we can use whatever hardening rule we want, isotropic hardening or kinematic hardening or nonlinear kinematic hardening, what have you. We can do all of that, and we can directly relate our nominal stresses to our notch root plastic strain. Right, so if we have an entire time history of our axial stress and our torsional stress, torsional nominal stress, it can be completely non-proportional because we're using this yield surface approach that allows for non-proportional type loading. And what we get out of this then is a time history of notch root plastic strains. So this might be our axial strain. Our elastic strains can be determined through the Hooke's law, of course. So we get a total axial strain history. We get a total hoop strain history. We get a complete shearing strain history at the notch. Now, what are the downsides to this approach? Well, if you have a whole lot of plasticity, then there's no enforcement of equilibrium. Equilibrium is assumed to be where you have a little bit of plastic behavior surrounded by mainly elastic material. So you don't want to have stresses, nominal stresses, that are just too crazy, too high. Of course, from a fatigue point of view, if you have really high stresses, you're yielding a lot of material, your fatigue life is going to be very short anyway. So from a practical application point of view, this idea of the structural yield surface is pretty nice, pretty neat. Now, if we wanted to go back and find out what our notch root stresses are, well, then we use a strain input plasticity algorithm, and then we calculate our notch root stresses. So we have sigma at the notch, we have sigma hoop, and then we have a shearing stress at the notch. And then we can get all of these as well. Once we have all that information, then we can put that into our critical plane fatigue calculator or whatever calculation algorithm you have, depending on the type of loading that you've got. If it's proportional loading, then you might not have to use something as sophisticated as a full critical plane model. But if you did have that level of detail that's required in non-proportional histories, then you can do a full critical plane analysis once you have the notch root stress and strain histories. And so I think this concept is neat. And I came up with it in conjunction with my advisor, Daryl Sosi. There is a kind of an issue maybe with this, and that is in some cases, and we've talked about this already, in some cases it's not very easy to define a nominal stress in axial loading or a nominal shear stress. So this S axial and S torsion can be kind of tricky to define. There is a way out, and this was noticed by another person I was working with at the time, Volker Kutkin. There is a way out of this, and it's the fact that the stress concentration factor works together with a nominal stress to produce the elastic notch stress. So in fact, we don't have to use a definition of a nominal stress. We can use our nominal stress as the actual elastic or the pseudostress at the notch. So let's describe that just a little bit. All right, so the elastic stress itself at the notch would be the stress concentration factor times the nominal stress, Kt times S. We could put a little E by it, by that sigma, and that's called the pseudostress. And we can in fact construct our yield surface in terms of pseudostresses. E sigma ij is the pseudostress tensor. So that incorporates all the effects of what goes on at the notch in the elastic range of the material. Right, so again, if we go back, we can do any object we want now. But let's say we have a finite element model of our notched bar like this. We're to pull a little cube out of this material. No matter what the loading is, I can find a stress in this direction. So maybe this would be our nominal axial loading. Okay, so that nominal axial loading gives me a stress in the axial direction and a stress in the hoop direction. If I have the same situation with the bar in torsion, then on my little block like this, I have some shearing stress. Maybe I get some axial stress in there somehow too. If I have another load, maybe bending, then I can get various loads. But the idea is each of these different stresses then can be calculated based on elastic behavior of what goes on at this notch. We've talked already about this idea of linear superposition. If I have loads that, if I have multiple loads, say maybe this is tension and torsion. If I have a load time history of my tension and my torsion, okay, I don't need to do an entire finite element analysis of those two time histories of load if linear superposition applies. If it's elastic, all I need to do is I need to do a single static finite element analysis. Do a little better than that. I can do a single static finite element analysis of each of these individual cases and then apply superposition. Okay, so this corresponds to this case, and if I have the same bar, I do a completely separate static FEA, and I do torsion, that would correspond to this case. Basically what I'm doing is I'm finding the influence coefficients for each of those separate loads. Those influence coefficients times the load history will give me my local elastic stress history. And if everything is completely linear elastic, this is a very, very common way to do this in finite element analysis. And this is the beginning of this paper, Pseudostress and Pseudostrain-based approaches to multiaxial notch analysis. Okay, and then it goes and talks about here are the influence coefficients times the different load histories. There's a little bit of talk about basic Neuber's rule. There's talk about this idea of the structural yield surface that we talked about. But the kind of the new idea and really the implementation that makes this more practical from the idea of finite element post-processing is that now we can express our structural yield surface in terms of the local elastic notch root, elastic pseudostresses. That's the word I'm looking for. Okay, so now here's my yield surface in terms of E sigma ij. What we still need is we need the axial pseudostress, notch root plastic strain curve is input. Where do we get that? Well, same as before. Neuber's rule, Glinka's formula, elastic plastic finite element analysis, or a measurement. But this idea of this yield surface and this plus the normality flow rule and we have a more general approach that doesn't depend on a definition of a nominal stress to calculate our notch root plastic strains. Okay, so we start off with our E sigma ij. It's determined from our influence coefficients times our individual loads each of these correspond to each other. So the Cij corresponds to load Li. We add all of these up to get the total time history of pseudostress. Once we have our time history of pseudostress, then we use our plasticity algorithm to calculate our notch root plastic strain. And the elastic part comes from regular Hooke's law. So let's, this is just our total strain history tensor. I don't want to confuse that with time. Let's just leave the superscript off of it. Epsilon ij is a function of time. Once we have the notch root, epsilon ij is a function of time, then we go back and we throw it in another algorithm to calculate our local elastic plastic stress history. And then once we have that, we have everything we need to do our critical plane approach. So the idea between the first and second paper that I showed are very similar. It's just that the second one is easier to apply in a production environment where you're actually trying to implement this into a tool that engineers would use along with finite element analysis. There's all kinds of tricks that can go along with this to make your processing, your post-processing for notch plasticity more efficient, and that is in another paper. See if I can find that. Yeah, here it is. Structural strain analysis, non-proportional loading suitable for FEM post-processing. So in this paper, we go through, and Volker Kuchen was very familiar with this type of technique, and so he was able to show some methods, talk about some methods to speed up the process of this determination of the local hotspots in a finite element model where you might need to do multi-axial post-processing. Not all grid points, not all nodes in a finite element model do you have to do that. It's only just a few that really kind of show up, or certain ones where you might have to do this full multi-axial analysis. All right, so with that, that kind of concludes our fatigue analysis course. May come back and add a few more videos at some point. But I hope you had a good semester, and take care.